So our next speaker in Lean Together 2025 is Damiano Testa. He's at the University of Warwick, and he's going to give us an introduction to linters. Take it away, Damiano.
Well, thank you very much for the introduction and for the opportunity to speak here. What I want to talk about is linters, which is something that I basically found out that what they were about a year ago, maybe. But I find them a lot of fun. So that's not what I consider to be my training, but it's something that I enjoyed working on. Okay, so let's see what linters are. So I assume that you know as much as I knew when I started this, which is nothing. So hopefully this will be clear. And if you have any questions, please interrupt me, because my goal is not to get the last slide, is to get some ideas across. So if you have questions, please interrupt me. Okay, so linters are something that has existed in computer science since the 60s. Wikipedia has an entry about it, and you can see that this is some piece of code that's supposed to examine other pieces of code and give reports on them. Okay, so it may inform you about bugs, errors, typos, whatever some other computer code can decide is wrong in some previous computer code. Okay, so. And this was used initially by Stephen Johnson to debug the Yak. So you see it's some very serious material here. And if you've used Mathlib, you might have seen, or you may or may not have realized, that there are two kinds of linters that are, at least in Mathlib, that are active, or that in Lean are active. And one kind is environment linters, and the other one is syntax linters. And the first half of my talk will be basically saying something about both. But ultimately, I will focus on syntax linters. So let's see a little bit what these are and what their differences are. So first, some general data about these things. So there's 17 environment linters and 29 syntax linters active in Mathlib. That means that they're either defined in Mathlib or in some dependency. Some of these are defined in core, some of these are defined in batteries, and quite a few of them are defined in Mathlib. So what do they do? Well, superficially, they're just code that can basically do whatever you want. So they're not very different. And in fact, there's basically, I mean, you could probably get any linter to be whatever you want, given enough time. So there's really no difference essentially about them. They're sort of fully functional Turing machines. So abstractly, there's no difference between them, but they're designed to do different things, and so they'll be better at doing different things. So both environment and syntax linters actually have access to the environment. What the environment linters do not have is direct access to the syntax of the declarations. And I'll show you some examples of why that is useful, or might be, or how it may be useful for some things. And the other difference between them is when they warn you. So typically, environment linters are silent when you're writing code, and then you push the Mathlib and it gets linted, and you realize that something that you did where you're not supposed to do, and then you get a report on CI. Syntax linters are typically chatty while you're typing your code, which is both good and bad. But basically, when you get squiggly things and you're typing something and it says, oh, you shouldn't have done that, that's typically a syntax linter. So you don't have to do anything to make them active, or basically someone else has already activated them for you. But once they're active, they're always active. And the other main difference is environment linters are more intended to be run at the very end of compiling something, whereas syntax linters sort of take you all the way. So every time you're typing something, the syntax linters are looking at it. If you've used Mathlib, you know that for getting the environment linters to fire, you may sometimes write #lint at the bottom of the file. And so that's somehow visually reminding you of the fact that you first write everything and then you lint it. Whereas syntax linters are usually started with set option, usually write set option before something, and then from then on you lint things. So that's how the perspective for them are. Okay. So let's see, in order to sort of get a little bit of a distinction between what the environment and the syntax linters are, let's see what happens in Lean when you type something. Okay? So for instance, we're trying to type, sorry, we're not trying, we do type example true given by trivial. Okay. So this is a very simple kind of command, so what happens when you type that? Well, Lean takes what you've written, so the string, and it first of all tries to convert it into a syntax tree. And I've pasted here some picture of what the syntax tree for this declaration looks like. Okay, so it's some fairly complicated object, even for something as simple as this. And then once it's created this sort of tree-like structure, it goes on to say, well, what do you mean when you say example true trivial? So I've converted it to some other shape, but what do you mean? And so then it goes on with elaboration of what you did. And so it's going to realize that true, the expected type, is some type. So it elaborates that to some type, so some other tree-like structure. Expression, so some tree-like structure. And similarly, you've told Lean that true had a term that was called trivial. So now it goes on and creates another expression for that thing. And the thing that it creates are much smaller, as you can see, than the syntax tree that you started with. This is not a rule, but in this case, this is what it is. And so you see, you went from having typed your short thing, Lean made it something bigger, and then it converted to some other thing, and you have now these two other tree structures that are just single leaves, essentially, the constant trivial and the constant true. At this point, Lean will do lots of checks, for instance, to make sure that indeed the trivial is a term of type true and sort of all sorts of things. So it does all of these things, lots and lots of work behind the scenes. And eventually, once it's done doing all of this work, it discards everything because you told this was an example to Lean, so it's not going to add it to the environment. It's not going to do any persistent change with this. And so basically, it did all of these computations, and then it retained nothing in the environment. Okay, so, and this is where you might start seeing a difference between environment linters and syntax linters. Lean produced the syntax for this command, the one that you see here. It produced transiently these expressions that represent the type and term that you've told it to create, but then it throws them away. It never stores them in the environment. So a syntax linter would have access to the syntax, but an environment linter would have access to basically nothing from this example. Okay? So this is one thing where syntax linters may do something where environment linters would have a much harder time to act on this. Okay. So let me continue. So this is what I was saying. So environment linters just see the outcome of all of those computations, which was basically I've done nothing. Where syntax linters see the process as it unfolds in some sense. So other examples of things that an environment linter wouldn't see, but that a syntax linter would see is, suppose at some point you wanted to see how your types looked like more in details. And you might set the option that PPAll, so the pretty printer, should show you everything that it has. That's something that an environment linter would notice. It would detect that you've used that command, but an environment, sorry, I'm not sure whether I said environment or syntax. A syntax linter would notice this, but an environment linter wouldn't notice that. Or I guess it might, but anyway. As I said, everything is complete. They can all do everything. They could reproduce Lean itself within them. So they can, of course, realize that this has happened. In the case of the option, maybe this is not a perfectly set example that does leave a trace in the environment, but the environment linter wouldn't know where this happened. It would just know that the option is set. If you type lemma instead of theorem, that is basically invisible to an environment linter, but a syntax linter will see that you actually type lemma instead of theorem at some point, and so it will notice that. And even more internally, if you're proving something with a tactic, the tactic is code that produces a final term. The environment stores the final term, but the tactics that were used disappear from that. And so if you use the non-terminal simp, an environment linter wouldn't detect that. It would just know that you've proved it, and it wouldn't even know that you use simp to prove it. Whereas syntax linters would realize that you actually typed simp at some point, and that was a tactic, and that it did something. So these are some of the things that distinguish them. And as I mentioned before, you have to remember yourself. You have to remember to activate environment linters. So you actually have to do something. Whereas syntax linters are always live. So you may want to silence them. So you may have to do something explicitly to get them to shut up. But you don't have to remember them typically. They're always live, and they're always doing something for you. Okay, so maybe something for you or something against you, but they're always doing something. Okay, so overall, what's the use that you have for these things? So you build your whole project, and when you're done, you run all the environment linters, and you make sure you haven't done anything silly, or you haven't done anything that you weren't intending to do. Now, this is great for checking things like simp normal form. That's an environment linter. If you decide to add or not add the simp attribute to some lemma somewhere, that's going to affect how things will behave later on. Simp will become stronger or weaker depending on what you add to the simp set. And you may not want to label with the simp attribute a lemma that simp already proves. And that's what the simp normal form linter does. And for that, it's useful that it has access to every declaration that is being built, that is being declared, and that you do sort of these comparison checks so that you're not labeling too many things same, that you're not labeling things that simp will never work on, and that you're sort of doing some sort of reasonable kind of things with the lint attribute, with the simp attribute. So that's certainly something that an environment linter would do better than a syntax linter. But when you get to the stage where you're checking everything with the environment linters, you will have had to endure all the syntax linters before that. So they will already had a chance to tell you, you shouldn't be doing this, or you should be doing that, or please silence me because I'm getting annoying. Okay, so this is what where somehow they fit in the process of producing code. So let's see how we can use linters to do the sort of simple task, like maybe figuring out how many examples Mathlib has. And I've chose example just because it's what I talked about before, and it's something that an environment linter would have a hard time detecting. So I'm going to focus now on syntax linters. But I mean, I don't know whether this would be your first reaction, but at least my first reaction, if I were asked how many examples there are in Mathlib, I would grep the repository and figure out how many examples how many times the word example appears. And so you can see what happened in Mathlib a couple of days ago when I wrote these slides. And you look for example, and you see 1,500 hits. And you think, well, a lot of these things might be sort of example in docstring that says, for example, we do this. And I don't want that. I want the actual command example. So then you say, well, okay, let me at least rule out all the things that are examples or example comma by adding an extra space after it. You sort of decrease by about a third what you had before. And then you say, well, let's probably, if I have an example, it's going to start the sentence. So it's going to be at the beginning of the sentence, and then it's going to have a space afterwards. You half again what you had before. And so you kind of start thinking, well, now what else should I do to make this more robust? I say, well, the example could be a non-computable example, then it wouldn't be counted by this. But on the other hand, there are sentences that have examples that begin with it because of how the sort of line breaking is working. So maybe these two things compensate. So maybe we do have about 500 examples in Mathlib, and that seems like a reasonable estimate. But how would you go about doing this really? So how many examples really are there in Mathlib? So now it would be good if we had access to something that could detect whether the word example written somewhere was example because I'm in a docstring or because I'm actually typing the example command. And so for this, let me go back to the example that we had at the beginning of the syntax tree for example. And just for comparison, let me compare it to the same basically result, but written as a theorem. So you see the theorem side is a little bit longer. The one on the right is the syntax tree for theorem. It's a little bit longer. Well, the theorem must include the name of the theorem, so it's not so surprising that it's a little bit longer. There are some subtle differences here and there, but you can see that the declarations start the same, this first part here. By the way, all of these nodes with null things, these are if you had, as I was saying before, a non-computable example or a partial or non-recursive, or maybe you had some attributes to this. These would all sort of populate these fields here. So they're all empty because I didn't type anything before example, essentially. And then here you see there's a difference between example and theorem. So if I had access to the syntax, I might just go ahead and say, well, look at all the commands that you have and see if you ever have a node that it's called, or that has the syntax node kind, that's what it is, that ever has lean parser command example. And if you have it, count it, and otherwise don't do anything with this node. And so I did this experiment, and it turns out that there are 387 examples in Mathlib. Okay? So our estimate was okay, but it was not really good. And now, in fact, once I have this written up, I may make the linter do other things with that examples. Once it locates them, it could do other things. It could say, well, are they long? Are they short? Do they use tactics? Do they use term mode? So you can then do further filters on this. So this is an example of how you might be of a use that linters might have. So what other things can you do with linters? So of course, we may not care that much to know how many examples there are in Mathlib, but these are some of the linters that are in fact present in Mathlib. So there is a linter for duplicated namespaces, for tactics that you wrote, but they were never executed, or they never did anything, which you might be surprised. When the linter was introduced, I removed several hundred lines of tactics that were in Mathlib but not doing anything. At some point, people decided that they wanted to remove the refine prime tactic in favor of refine. So that's one situation where you could have grepped for refine prime, and maybe in this case you would have gotten very good hits. But a linter was helpful for this. People don't like to use admit instead of sorry, so there's a linter for that. People don't like to use a $sign instead of the less than vertical bar sign. There's a linter for that. The focusing dot is supposed to be typed with a center dot, not a dot. There's another linter for that. You can look at variables that are not used. You can look at files that are too long, lines that are too long. You don't want to import too much. You don't want to set options in Mathlib. All of these things, they're all done with syntax linters. And there's lots of things that is going on behind or in front of the scenes that you may or may not have noticed. Another thing that linters can access is info trees. And I'm going to delay talking about these for a little bit because there's a lot to say about them and they're sort of become very technical, but that's something that I didn't really talk about, but that is also very useful. Just let me see how I'm doing with time. So it's unlikely that I will have time. So just very briefly, info trees basically encode everything at all. I see something that included the archive, but let me point out that I grepped inside Mathlib. I made that mistake before, but I did grep inside Mathlib, so it's not bad. So info trees basically store, they store a lot of information inside the syntax tree or in some sort of other structure like the syntax tree and info tree. And they basically give you access to expression things. So I talked about the syntax linters and I talked about what the syntax that Lean produces, but Lean at the same time that it's producing the syntax, it's also producing term information and it's mixed with tactic information if you're using tactic mode. So all of these things get built somehow together, and info trees access everything. They see the syntax, they see the term, they see the tactics, they see the commands, they see a lot of stuff. So and linters have access to that. So linters also see that. So that's what the info trees are. Okay, so as a sort of example, let me talk a little bit about the min imports linter, just because it's maybe a little bit different from the very initial definition that I gave, which was supposed to flag errors or bugs. And the min imports linter is a linter that is that tells you when imports have changed. So as you're typing commands in Lean, or you're typing declarations, you're developing some formalization for some project, not every declaration uses all of the imports that you have. And so the min imports linter keeps a tab of what imports have been used so far by your file. And with each successive declaration, it compares the imports that this new declaration needs with respect to the previous ones. And if it needs more imports than the previous ones, it just tells you, hey, I had to use this other file, and it was not enough to use the previous ones. So this is highlighting something where and it's good that, I mean, I don't know whether it's good, but it's sort of timely that today there was an issue with the min imports linter. So this linter is using information from running on the previous commands to deduce information about the current command. Now, there is a very strong limitation that syntax linters have, which is that they can do everything basically they want on the environment while they're running. But as soon as the processing goes to the next command, everything that they did disappears. And so they leave no trace in the environment of their action. If you've seen the movie Memento, is like being the main character of Memento. You have no idea what is going on around you. You just know what you've lived in the last 5 seconds. So in this case, the linter needs to have access to what the previous command had used as imports to say whether it increased or didn't increase from the previous one. And so there's a bit of a trick in order to do this, which is to store that information in something that isn't something that is stored in the environment, which comes with a cost. That means that the linter expects the file to be parsed linearly, so from the beginning to the end, and not doing things jumping around. And so editing a file, for instance, would be bad for this linter. And probably this might be what happened today with the linter. If there is now non-linear execution of files, that might also cause problems. But this is a limitation of linters that may or may not cause problems. So that's what the min imports linter does. But in some sense, it's not really about good code. It's mostly about, am I developing a good library, which in some sense is also good code, but it's maybe more global of a point of view than just figuring out how I put the spaces in the right places, or should I use parentheses there. So linters can also help with that. And then just to give an idea of what other things linter might do in the future, or what is sort of being developed, what is maybe sort of developed but not maybe such a good idea. So there's a linter that is supposed to be useful for beginners, that a lot of the times, or at least I remember when I was surprised that 1 minus 2 in Lean wasn't -1. I now know that this is the case, and I know what the root cause of this is, but it's not so easy, and people often ask on Zulip about that. And so I actually have a linter written that would check whether you're using NaT subtraction, and it will just tell you, hey, you're using NaT subtraction. If it doesn't find the assumption that the thing you're subtracting from is smaller than the thing you're subtracting from, it would just tell you, hey, you know, this doesn't mean what you might think it does. Of course, this wouldn't be a linter that is always on, but it might be useful if you're learning about the thing. You turn it on and you get a lot of extra warnings about things like this. Another thing that it might do is if 2 types are printed the same and you get a warning that says fail to synthesize this because this thing is not equal to this other thing and they're actually equal. It might tell you, hey, they may look equal, but they're not actually equal. So these kinds of things would be in scope for the paper cut linter. As I said, it's a prototype, it's working somehow, but it's not active. It's not even in Mathlib. There's another linter that does some testing for tactics. So this is meta programming. You you want to test whether a tactic is robust. So you write a test suite for it, and then you run this linter. This linter runs more tests on the tests you've done. And it discovered a few things in Omega, it discovered something in Ring, it discovered a few bugs somewhere. Mostly minor things about not doing the right thing with the context, or forgetting to look at the right transparency level, but sort of it discovered something. In the spirit of the min imports linter, there's a refactors linter that might help figuring out not what the imports are needed, but exactly the trail of declarations that are needed in order to get something running. So that might be useful to extract minimal working examples or minimizations of bugs, or just breaking the library apart. I want to have all of the analysis library, but remove everything that isn't needed for analysis. That's another thing that this could be doing. Then it could lint no linting things. So this is meta linting. It could look at whether you use the command that wasn't needed, whether you have a variable that is never used, the set option that is never used, whether you have a no lint that is not used because maybe it was at some point that someone changed the code later on and forgot to remove that no lint. So these kinds of things are in scope for linters. Something else, sometimes you open it with a variable, you add two type classes that are sort of implying one another, like additive add on R and ring on R. A linter may warn you that you've done that and say, hey, you already have an additive structure on R. Are you sure you also want to put a ring structure on it? So these kinds of things would be in scope for linters. Right, so syntax info trees, I think I have 2 minutes, so I might not talk about info trees anymore. It's what I said before, maybe a little bit more. Now, I want to talk a little bit about the costs that linters have and when they are useful and when they're just a nuisance. Of course, whether they're useful or not depends a lot on what you're doing. And depending on what you're doing, you may or may not want to have some linters active. And I sort of wrote there a few instances where you might have very different opinions on whether you want to be warned about the fact that you're missing a header for your file. If you're making a PR to Mathlib, you definitely want to know that because you'll be told at some point anyway, so you might as well push a PR that already has a header in. But if you're teaching a module, you're giving a presentation, you probably don't want to be bothered by the fact that, hey, your file doesn't have a copyright file. Like, who cares? That's not the point. Whereas if you're teaching a module, you might be very happy to have Lean tell you, hey, you shouldn't use have here, you should use let. But that may not be very helpful if you're sort of an experienced user and you know you want to use have, even though let would have been more appropriate. So that's another example of something that you shouldn't want to have. And the doc prime linter that no one really likes. So I just put it there because everyone hates it and it's never good. And then in terms of performance costs, well, of course, because you're running code on every command, those are very important. I'm not very good at writing very performant code, so hopefully I will learn something and maybe talk about it some other time. But they certainly are concerns that you have to be worried about. You can execute whatever code. You may not want to spend 10 minutes to know that example true is trivial was actually what you wanted to type. And that's all I wanted to say. Thank you.